Hello everybody, I'm here to talk today with you about cloud native applications on OpenShift and Azure, but first let me introduce myself. My name is Edson Yanaga, I'm a Microsoft Azure MVP and I'm also a Java champion. Currently I'm also a Director of Developer Experience at Red Hat, and my Twitter handle, just in case you want to follow me, is @Yanaga. But I really like to introduce myself as a software craftsman, and the best definition that I have about a software craftsman is somebody that cares about his job, and I really care about trying to help developers worldwide to craft better applications and to help them to deliver better software into production faster and safely. So I really like to talk about DevOps, microservices, Java, and .NET on Linux best practices. So just in case you want to follow me, that's my main point of discussion. So check my Twitter handle @Yanaga. And just to set some expectations about the level of this section, we're not going to dig deep into the subject of cloud native applications. Instead, I want to picture for you an overall situation of what is a cloud native application and some different ways that we have to craft these applications and to deploy them into production. So I'm gonna choose just one single topic in the entire subject of cloud native applications and show how our life can be much easier when we have the right tools for developing this kind of application. First, let's try to define what is a cloud native thing. So it seems that there is a lot of confusion these days about what is or what should be a cloud native application. So I'm gonna check the definition from another place, which is the Cloud Native Computing Foundation, which is a non-profit organization composed of many individual members and also big companies like Docker, CoreOS, IBM, Google, and Red Hat. Just in case you want to check this website, cncf.io. And the definition that they provide for us for what should be a cloud native application or what is a cloud native application is that cloud native applications, or simply cloud native, is a new pattern of application development that considers portability and designed to run in the cloud. So in the cloud you have a lot of capabilities that you didn't have on premise or even virtualized before. And also it means that it should be portable, meaning that you should be able to port your applications from one cloud provider to the other, from one environment to the other, from one container orchestration platform to the other. And so that's one of a big picture of what should be or what is a cloud native application. And also cloud native applications or cloud native architectures, they have three main common attributes. First, they should be container packaged, meaning that the application and process should be run in software containers and run and deployed as a single unit, which usually facilitates transparency, resource isolation, allows you to easily reproduce your application environment in different staging environments. For example, you can have the same environment in development, into staging, into production. It is easy if you package them as containers. Usually also cloud native applications or architectures are dynamically managed. So it means that you can move your containers from one host to the other. You can scale them independently depending on demand. So you have, if you have some containers that are not being used at all, maybe you can reduce the number of instances that you have in production. And usually this kind of dynamic schedule and management helps you to improve your resource consolidation, which helps you to also reduce costs because you need less infrastructure, or just in case you're using a public provider just like Azure, it will also help you to reduce your costs. And also it means that cloud native applications are usually microservices oriented, which means that they are usually defined as loosely coupled artifacts, and they communicate with others using some kind of communication protocol. And if you design them well, and if you have really loosely coupled artifacts in your system, then usually you have more agile processes, and you'll be able to deliver software more often, which will reduce your batch size. And since with every discussion around DevOps, if you reduce the batch size, you're improving a lot your feedback loop, and you're also improving the quality of the software that you deploy into production. I'll pick two special projects from the Cloud Native Computing Foundation, which I believe they are important. First one is Kubernetes. Kubernetes quickly became the de facto standard for container orchestration platforms in production. So in recent research, they consider that approximately 72% of the companies are using Kubernetes in some kind of environment, being developing, staging, or production. So that's a real good data for you to consider. And we also believe that Kubernetes is a good environment for deploying containers in production because it's based on the same technology that Google uses to deploy approximately 2 billion containers into production per week. So if Google can handle that amount of containers into production per week, maybe we can schedule in our enterprise application like our 50 or 100 or 200 containers in production safely too. If you want to check more information about Kubernetes, you can check their website, k8s.io or kubernetes.io. You see, it's easier to spell and say KAS.io. So it's a very cool container orchestration platform. And if you're an Azure user, you also have the possibility that Azure Container Service, you have different container orchestration platforms for you to choose. I strongly suggest you that you give a try to Kubernetes because it has very cool features. I'm going to show some of them today, and I'm going to show how Kubernetes can solve many of the different problems that we have when designing microservices and distributed architectures around your artifacts. And the other cool project from the Cloud Native Computing Foundation that I want you to check is Linkerd. Linkerd is a recent addition to the Cloud Native Computing Foundation. So it's a new thing that people are discussing these days. And I chose particularly this project because I believe it has very nice solutions for some problems that we face every day when dealing with distributed architectures. So let's check on it. And it's not a Cloud Native Computing Foundation project, but I really want you to check on Red Hat OpenShift, which is a platform as a service. And when I say platform as a service, I want you to take care because usually PaaS environments have a bad reputation because we have some PaaS in the past that require you to change your current applications to run on the PaaS and everything else. But instead, OpenShift is a layer on top of Kubernetes, which provides you some features and functionalities that help you as a developer to deliver more easily and faster your software into production, and also provide some nice features for running your containers into production too. We're gonna cover that also in some minutes. And of course, for you to check, I've deployed an instance of a Kubernetes cluster and an OpenShift cluster. You see, every OpenShift cluster is also a Kubernetes cluster because OpenShift is just a container running on top of Kubernetes. And I've deployed successfully all of this complex cluster on Azure very easily. In fact, I'd like to testify something, the beauty of open source, how open source has won the world. And it's very nice to be seeing that Microsoft is embracing open source too. Because Microsoft provided on their Azure Quick Start templates an OpenShift origin template for me to deploy easily my OpenShift cluster on Azure. I've tried that, but due to recent changes on Ansible, which is the tool that is used by OpenShift to deploy the OpenShift cluster on any platform, the template on Azure is broken. But since it's open source and it's available and the source code is available on GitHub, I was able to fork it. I performed some changes, which took me like 2 days to figure out because I had to dig through a lot of different points of the scripts. But then I was able to check where the bug was. I was able to create a workaround around that. I've patched the templates, the scripts template. I committed that. I published it on GitHub, and I was able to easily just with a single click to deploy this template, which is a kind of complex template because you have different nodes, you have a master node, you have different hosts for running your application, you have load balancers, you have virtual networks, and you have permissions and everything else. So it was very easy to set up once I had the proper template. So if you, just in case you want to check my version of the template, which is working on the current version of OpenShift, you can check also in the URL below, which is on my GitHub account at Yanaga. I'm going to submit a pull request to the Azure repository, which I expect them to accept because now it's working. So expect to be in the next few days or weeks to be the patch working also on the Azure Quick Start template. So that's my testimony. Later I'm going to show the OpenShift running on Azure, which I deployed using this particular template. And why should we need a platform for running our microservices or our distributed applications on the cloud? Usually we have a set of problems when we're running monolithic applications. And when we're running distributed applications such as microservices architectures, we have a whole new set of problems to deal with. And I like this quote, which I took from the Linkerd website, which is the source of most of the complex, surprising, emergent behavior was usually not the services themselves, but the communication between services. And Linkerd was built on top of the experience of people developing software at companies like Twitter, Google, and Microsoft. So they gathered a lot of this different knowledge and implemented them on top of Linkerd. So what we have usually when we have a distributed system, we have complex problems to solve using code, but the most complex things to solve are usually provoked by communication problems in our infrastructure. So we probably better rely on some really good tools to help us to prevent first, and then to identify these problems into production more easily. In this slide, I want to show you just some, because we have much more, but I chose you just 7 ones because I believe this. If you're starting to think about microservices, this one should be your primary starting points for thinking about a microservice architecture. So usually when we're talking about distributed systems in general, and of course microservices in particular, we need to deal with centralized configuration, we need to deal with log aggregation, we need to deal with health checking, service discovery, circuit breakers, tracing, and monitoring. Okay, which means that centralized configuration, I need a single point in my system where I can have my configuration and make this configuration to be propagated through all of the running container instances in my system. I also need log aggregation, because now that I have more than one instance of an application running in a distributed environment, and I don't want to SSH into each one of these instances to check the logs to see what is happening. I need a platform that aggregates all the logs for me, so I can check in a single place all of the logs and potentially index the logs later for me, because I want to search them. I don't want to scroll the logs to check the information that I need. I also need some kind of health checking, because I need to know if my container is running correctly or not. I can't rely on manual checking because I have too many moving parts to be checking. I also need some kind of service discovery, because if I have just one single application, it's easy for me to remember the endpoint that I must access. But if I have like 10 different artifacts on my application, and each one of these artifacts has like 3 or 4 different instances running to production, I don't want to be able to locate each one of the instances of each one of these artifacts. So I need some kind of service discovery for me to be able to easily identify, check a name, and just get the endpoint that I want to access. I also need some circuit breakers, which is a topic that I've chose to discuss today, which is your capability to be resilient when something goes wrong in your communication or in your remote endpoint. We're going to check more deeply later. We also need some tracing. Before that, you could debug your application. If you had a single code base, you could debug your application, because that's a monolith. You can see what is going on method by method, line by line. But now that we have distributed applications, your request came from an artifact. Now it's requesting some information from another artifact. Your request is going to that other artifact. You just lost the stack trace. So you need to be able to trace your requests on one endpoint to the other endpoint, where did my request go in a particular transaction, how much time did it took to go from one endpoint to the other. So these are the things that are required when dealing with distributed systems, and tracing is fundamental. We need to have some form of easily tackling the problem of tracing. And of course you also need monitoring. With a monolith, it's usually easy for you to check if the monolith is running or not. But if you have many moving parts, and if in general your system is not performing well, you don't want to check each one of the instances of your multiple artifacts into production to check where is the problem. You need a monitoring platform for to show you some statistics. Usually monitoring means, in a microservice architecture, means not only checking if your artifact is alive or not, if your instance is alive or not. Usually you have to monitor also things like business metrics to check if everything is going well or not. So these are some of the points that we might want to consider, and how a platform can help us to solve these problems. So some of these problems can automatically be solved by your platform, the platform that you choose. So if you choose to run your applications on Kubernetes and OpenShift on top of Azure, you automatically have added to your system centralized configuration, because Kubernetes has a feature called config maps. Log aggregation, because OpenShift automatically aggregates the logs for you, and you can easily add some templates that will add your favorite indexing engine for logs to you too. You can choose what you want, how you want to index your logs. You also have built-in health check provided by Kubernetes, and you also have built-in service discovery provided by Kubernetes. And when I mean service discovery, I mean the most reliable and simple service discovery mechanism that we have invented so far, which is just DNS backend names. And for the rest of the problems, circuit breakers, tracing, and monitoring, we can tackle some of them with Linkerd. So Linkerd is the novel approach that I'm going to show you today of how can you solve the problem of circuit breakers and tracing, easily adding without having to change the code of your application for dealing with that. And monitoring, well, monitoring is a very particular characteristic to be dealt with. So I'm not going to cover this today, but I'm sure that each one of you or us have their favorite monitoring platform. So maybe we can discuss that in another session. So from all of the topics from microservice characteristics, I chose circuit breakers to discuss with you today. So circuit breakers, you're thinking about maybe it's related to the physical circuit breakers that I have in my house to prevent some fires from happening if I have some electrical problems in my house. You bet, that's exactly the analogy that we're gonna use on circuit breakers. So usually when everything is working fine on your application, you have requests coming to an artifact, you need information that is in another artifact, you just issue another request to your artifact, you wait for a response, you process, you get the result, you process the information, you give the information back. So that's when everything is fine and the circuit is closed, because everything is working well. But then something happens in your distributed systems. Somebody deployed a new version of your remote artifact that you were accessing. Now it started to fail sometimes. Now it started to become slow in some kind of requests. You can allow that's the single point of problem in your system to break down your entire application. So what you're going to do, maybe in some kind of situation, if the application, the remote endpoint is not responding, or if the remote endpoint becomes so slow, you want to open the circuit, because you don't want that problem to be propagated to the other endpoints. Your endpoint that you're coding now must be resilient, must not propagate failure from one remote endpoint to the others. So how can we do that in our application? If we must design our applications to be resilient, how can we deal with that in our application? I'll show you two different approaches for this. First, we can implement circuit breakers with code. So I'm going to show you now some Java code. I chose Java because that's the language I'm more comfortable with, but also we could have done that with .NET too, or even Node.js or anything that you want to. But I chose Java particularly because the most popular circuit breaker library in these days is the Hystrix library, which was created by Netflix. And since Hystrix was originally created in Java, and now it's being replicated in other languages such as .NET and JavaScript, I'm gonna stick to the original sample with Hystrix. So if you think about Hystrix as the circuit breaker implementation, you have a very simple code here. You have a Hystrix sample that I've just created, which extends a Hystrix command. I have some keys here. So in the constructor, I have to pass a string, which will be used later for me to show you the monitoring part of Hystrix, which is very interesting too. And basically everything that you want to do in your code here, the main method of a Hystrix command is this run method, which returns the operation that I want to execute, which can possibly fail. So which kind of code do you want to put inside the Hystrix command here? You want code that can fail, and usually remote invocations, meaning that when you're trying to access a remote endpoint, the code that you're going to use to access the remote endpoint, such as issuing an HTTP request, you want to put that inside this method run. And just in case if anything goes wrong, Hystrix provides you this method get fallback, which means, oh, I tried to access the remote endpoint, it's failing, it's returning me 500 error, or it's taking too long. I specified in my Hystrix configuration that the remote endpoint should answer me in like at most 1 second, but it's taking me like 2 seconds to reply. So I'm gonna open the circuit because that's too long. I can't wait for that much. So instead of just trying to wait for the return of the method run, Hystrix will execute this method's fallback for you. And when I mean fallback, usually you're gonna reply with a default response or a cached response. For example, in the specific case of Netflix, you had the recommended videos on your Netflix account. But you know, recommended videos is not a crucial feature of when you try to watch videos. So instead of showing the user a blank recommended videos page, why not we just show them, instead of a target recommended videos for you page, why don't we show like default recommended videos for you? It's much better for you to see a default page rather than seeing a blank page or an error exploding in your face when you try to access the Netflix website. So that's basically how can you do things using circuit breakers on your code. And you bet, now you must be thinking, what? Now I have to change all of my business logic to be incorporating these Hystrix commands to be executing the default running situation and the fallback situation. I need to be implementing default responses, or I need to be implementing caches. Well, I guess that's true. That's one of the ways that you can do. You can implement resiliency in your application through code using some circuit breaker library just like Hystrix. Or you can use another alternative such as using infrastructure or sidecar containers like Linkerd to solve your problem. So how do we solve the problem using infrastructure like sidecar containers? I'm going to show you how it works. First, a diagram. So if you check the diagram here, you see that you can have a single unit of deployment. Usually you have your application running on your host or your pod if you're running on top of Kubernetes. You have your application instance. Then you have a sidecar container, which is Linkerd, which can be, you can consider a sidecar container, which is an ancillary application that is running parallel with your application. it doesn't have any functionality by itself alone, so it will never be running without your application instance. That's why it's a sidecar container. It's only worth to be running if your application is running. That's why we call it a sidecar container. So basically, instead of your application going to check the remote endpoints by itself, your application is going to ask Linkerd to go to the remote endpoint and check the results. Oh, give me the results of that endpoint and come back and everything else. So instead of you having to code the circuit breaking and the tracing and the resilience part of your application, Linkerd has already implemented this kind of thing, because Linkerd gives you out of the box many different things like load balancing, like circuit breaking, which adds resilience, also adds for you tracing. So you can rely on everything that is implemented on top of Linkerd already. So your application is going to be agnostic because it thinks that it's going to access a remote endpoint too. But in this case, the complex part of dealing with remote endpoints is already dealt by Linkerd. So you just access Linkerd, Linkerd gets the remote endpoints for you and adds you some very nice features which I'm gonna be able to show you today. So instead of just talking about what Linkerd could do for you and Hystrix could do for you, let's show some live application showing some behavior, how your application should be behaving when using either Hystrix or Linkerd. I want to start showing you the Azure Quick Start template for OpenShift, Orange, and RHEL. So this is my forked version on GitHub, but just in case you want to check the original one. So I was able to deploy an OpenShift cluster very easily on top of Azure. I just have to check this repository. I could deploy that directly using this button. It would just open a web interface for me on top of the Azure portal, where I would be able to just fill the parameters of the templates and it would automatically deploy the OpenShift cluster for me. So it can't be more straightforward than that. I particularly am a fan of command line interfaces, so I deployed this cluster using the Azure CLI, but feel free to use this button because it works for you too. Just be aware that we have a lot of different instructions. There are some preconditions that you need to execute before trying to deploy your OpenShift instance on Azure. So you need to generate some SSH keys, you need to create an Azure key vault, you need to know what does each one of these parameters means for you. And after you install your OpenShift cluster, you might want to check here because these are some optional steps that you might want to execute, but which will enhance your experience running your OpenShift and Kubernetes cluster on top of Azure. Okay, so check this template, is awesome. Hopefully very soon the workarounds and the corrections that I've created on my fork will be on the original Azure Quick Start templates. And after I successfully run and deploy that, in my particular case, it took me approximately 18 minutes to deploy. So you see, it's a cluster. You have a lot of different things to configure and to deploy. So you might want to take a coffee break after you start the deployment, because it can take some time depending on the size of the image that you choose. Of course, I strongly recommend you to choose some of the faster one with SSDs. It will improve your deployment time a lot. And after you do that, you can see here on the Azure portal, you have a lot of different resources that were deployed. You see OpenShift creates storage accounts, public IP addresses, availability sets, virtual machines, network interfaces, and etc. So there's a lot of resources involved, but luckily the template makes it very easy for us to deploy an OpenShift and Kubernetes cluster on top of Azure. After you have successfully done these steps, you will have this beautiful OpenShift console running on top of Azure. So you can log in with the user that you created on the parameters with the same password that you provided there. You can log in here. Here I don't want to save the password, and I already created a cloud native project inside OpenShift where I want to deploy my application and my sidecar containers using Linkerd. So for that I have to create that using the command line. And if you check here the command lines that I have, I created 3 YAML files which are responsible for the config map, the replication controller, and the service, which are terms related to Kubernetes, but don't worry, it's not that complicated. And I also usually advocate for cross-functional teams or full stack teams. So you want to have an ops person near you to maybe if you don't need to understand completely this concepts, but it helps you to have a basic notion of them. So maybe the ops people can help you to configure how it's going to run and behave into production. They're going to help you to craft these YAML files too. But basically I'm going to get the OpenShift command lines and create these resources with the YAML file. So I just have to do this oc create -f config to successfully create my config map. So oc get config maps. Gonna show that I have successfully created it. Now I'm gonna create my replication controller. And create my service. Just in case later, if you want to expose this application to the outside world or to the internet, you might want to create an OpenShift router for you, but that's another step which I'm not gonna cover today. If I successfully created all of these resources on top of Kubernetes and OpenShift, I can back here to the console. You see it's a live console, so all of the changes that I've created on the command line are already shown here on my web interface. As you can see that I have a service called hello, and my replication controller here I have 3 containers running, hello, Linkerd, and kubectl, and since they're all in the same pod, they all have the same life cycle. Here in the interface, I could do that also in the command line, but if I want to scale that, I can scale here using the web interface. So Kubernetes and OpenShift is going to schedule another instance to be executed. So let's check what happened here. I also have some very nice features. They are both running, but if I want to check, let me check into this pod. I can have all the information that I need from the pods and from the containers. I can have the environment. I didn't provide any, so I don't have any information here. I also have the logs. If I want the logs from the container hello, the container Linkerd, the container kubectl. So if I want to check in what's happening inside the container, I can open a terminal. You can see that the hello is running an Nginx instance. Linkerd, let me open it. It's running a Java process which is responsible for Linkerd and so on. I also have this very nice view of the events that is happening with this pod image and everything else. So that's the basic understanding of what's happening inside my Kubernetes OpenShift cluster. You can see it already scaled for 2 pods. If I want to scale them down, I can cut it back and Kubernetes will kill it for me. If I want to, scale down to 0 replicas, I'll have 0 instances running, so it gives me a warning. I want to cancel that for now. But I just wanted to show that it's not that complicated for you to deploy sidecar containers with your application to be run. If you check the YAML files here, let's check the replication controller YAML file. You see here you specify that you want 3 different containers. I want to run a Linkerd container. Sorry, that's a config map. I want to run a hello container, a Linkerd container, and a kubectl container. That's the basic information that you want to provide a config map, and you get used to that. But instead of just showing the deployment, this is a very simple hello. It doesn't provide you much information, but in order for us to explore what Linkerd can show for us, I have a simple application which is trying to issue many different requests to a running application with Linkerd, and it could plot some really nice graphics using Grafana. So let's open it up right now. So here we have how Linkerd can behave on your application. So we have an endpoint which sometimes can fail, sometimes can get slow, and everything else. So I have here 3 different configurations of Linkerd, which you can check by the graphics here. If I have Linkerd configured with no circuit breaking at all, you see the success rate. I have a goal of having 99% of success rate in all of my requests into my cluster. So if I run Linkerd here without any kind of circuit breaking, you can see that the success rate that I have over time is like 94, 93, 95. It doesn't get much better than that because I have multiple copies of my application running, and sometimes they fail, sometimes they get slow and everything else. So number of requests per instance and everything else. Now what happens when we add a circuit breaker functionality over our architecture with Linkerd? With the first option of Linkerd, which is just consecutive failures, I try to reach an endpoint, and if it fails 5 consecutive times, I consider it to be down. So I open the circuits, and I'm only gonna retry that instance again after some kind of 10 seconds, which is the configuration that I have here today. So you can see that when I add circuit breaker to my configuration, my success rate becomes much more higher. So now I have like sometimes 100% success rates, which is kind of perfect, and sometimes it falls down like to 93, 95. Okay, but it's much better. I have a much better success rate in this case compared to not using a circuit breaker. Okay, and you might check, how does it compare to the histories information and everything else? I don't have 100% success rates. Okay, just to inform you, it will be kind of rare or almost impossible to have a success rate of 100%, but you want to get as close as that as you can. So with a traditional circuit breaker, which is just take 4 times. If it doesn't respond, wait for 10 seconds until you try to hit that again. Because you know, when you have an instance of your application and it's already slow, it doesn't help if you just keep adding more and more requests to the pool, so your application can get even slower, which means if your application is slow or down, it's not worth in issuing more requests. You need the downtime. You need a back off time for you to not be issuing requests to that instance, so the application can recover by itself and become responsive again. So that's what this parameter does, the back off. And you can see if you have just a standard thing like consecutive failures, which is also the default thing for histories, you have a certain success rate. But now check what happens when we add another circuit breaker implementation from Linkerd. We have like a success rate. Instead of consecutive failures, we're gonna have a success rate of 90% of each 20 requests. So if I get 20 requests and the success rate is lower than 90%, I'm gonna consider that instance to be down, and I'm not gonna route requests to that instance anymore. I'm just going to route requests to the other instances which are alive and going well. In this case, you can see that the Linkerd success rate is much higher, getting almost to what we want, which is 99% always. You see when you have a drop here, it gets to 98.125%, which is kind of high and much higher than the other different approaches. Okay, so Linkerd gives you out of the box. You just have to configure these things on your config map to be able to, out of the box, without changing your application code, to have the circuit breaker functionality. And also Linkerd provides you much more, not only circuit breaker, but also tracing, log aggregation, and other things. But well, Kubernetes OpenShift already gives you log aggregation, but if you want to add another option to your pool, you can also use Linkerd. Okay, so that's a very nice simulation of Linkerd showing how different circuit breaker implementations of Linkerd can help you to improve your success rate on your distributed system. And just to show you the alternative, I have here a demo which we created from the Red Hat developers group. And we have a very simple distributed application which has some hellos. And here I want to show you, you remember that Hystrix code that I show you? Hystrix also has a dashboard which shows me also in real time the secrets that are closed, the secrets that are open, the success and failure rate, the back-off periods and everything else. So if you decide to do that using code, Hystrix can provide you also the information. You aggregate all of this information using this server which is called Turbine, which basically aggregates all of the statistics from Hystrix. But I would really want to show you now Zipkin, which is the tracing interface for. Here I have the Zipkin dashboard, which kind of traces the requests. So if I get here, you can see that I have a request here that went to an endpoint called API Gateway and went to an endpoint called Aloha, and it took this amount of time to process here. But this particular endpoint took like 6 seconds to respond. I have all of the tracings there, which is very important for me to use when talking about distributed systems. Let's test 7 spans. Okay, here now I can get the Bonjour service took 12 seconds, the Ohola service took 33 seconds, 24 seconds, 6, 1, 14 seconds. So you can see where my request came through. Each one of these requests has a transaction ID. So that's the basic things that you want to have on a Zip dashboard. You can instrument your code with Zipkin, which I have to agree with you, it's gonna be kind of complicated. Or you can have this out of box when you have an implementation like Linkerd. With Linkerd, you just have to point, where is my Zipkin server? And it's gonna stream you all the information that you need for the server for you to have all of this information. Okay, so that's the basic things that I wanted to show. You see it's running. It's not deep information, but I wanted to show you that you can have this. You can have the code version using Hystrix, which will provide you the information. You can have the sidecar container approach, which will provide out-of-the-box information for you with more sophisticated load balancing and circuit breakers than Hystrix, for example, and provide you integration with plotting engines like Grafana. Okay, so that's the basic overall. You can use sidecar containers at the cost. Okay, which is the downside of using containers? When you are using sidecar containers, you have to craft that YAML files, but the good thing about the YAML files, they all almost look alike. So when you're deploying your application, the next application that you deploy, the configuration is going to be extremely similar, so you can reuse all of this knowledge. So I'm a fan of using Hystrix. I'm a Hystrix fan, but currently I'm starting to think that sidecar containers are a better approach, specifically because it's not intrusive. You don't have to change your application code. So maybe you have that legacy monolith. You don't want to change the code of that legacy monolith. You just want to put that on the cloud, but you want circuit breaking, you want tracing and everything else. You can use a sidecar container for that. You might be convinced by now that you want to use Kubernetes and OpenShift and sidecar containers for your platform, okay? But talking about architecture, one of the biggest questions that I always receive when talking about microservices architectures is, what about my relational database? Because I have a monolithic legacy relational database running, but I want to dig into the microservice architecture. But how do I integrate data? How do I change that and split into separate microservices? How do I make zero downtime deployments using relational database too? I've collected a lot of different answers. I've talked to many different developers, with teams in many different parts of the world, and I try to collect many of the different possibilities for you to be dealing with this kind of problem. And I've written a book with O'Reilly, which is gonna be released today. And just in case if you're watching this right now, you can access this URL at developers.redhat.com. You can download the book for free as a courtesy of Red Hat developers, an O'Reilly book about dealing with legacy microservices database, relational database. So I hope you'll be able to enjoy all of this content. And last but not least, I would like to thank you very much for your time. It has been a pleasure for me to be at this event. Thank you, Microsoft. Thank you, MV Program. I have a lot of content around microservices and DevOps and everything else, and I had to choose a very small subject to be talking with you about this limited time that I have today. But I really hope to be able to engage with you, all of you, in another opportunity to be talking about even more also stuff that we can do with microservices these days. As again, if you want to check more information, please follow me and at Yanaga. And again, thank you very much and see you next time.